I've been working with my supervisor
Don't
for my
worry.
PhD. And so this talk is divided in these 4 parts. First, I'm going to expose the main objects that I'm going to discuss, which are dg-manifolds. After we explain the basic definitions, I'm going to expose a structure of an L-infinity algebra in the space of vector fields associated to a dg-manifold. And this first structure that I'm going to expose is going to have this property that it has a curvature term. After we finish this exposition, I would like to show the relation of the Fedosov connection that we expose for this construction with the operation which is defined on the jet spaces of vector fields. And I'm going to explain the relation between this Fedosov connection and the so-called Spencer differential through the geodesic exponential map. And for the last part of this talk, I'm going to expose a different structure, which is called Kaplanov type, L-infinity algebra. And the main property that this L-infinity algebra will have is that this will be not curved. So it's in contrast with the first structure that I'm going to expose. These L-infinity algebras are not having this curvature term. Okay, so first, to start, let me introduce the object. So a dg-manifold is a graded manifold M together with a vector field, which is nilpotent. So the typical examples of these objects are the space of differential forms. So we can regard these differential forms as a graded supermanifold. And in this case, the nilpotent operator is given by the RAM differential. So we understand the RAM differential as a homological vector field. And of course, we know that this satisfies the nilpotency condition. And secondly, in a very similar way, if we consider a Lie algebra G, then the Chevalley-Eilenberg differential will have this role of the nilpotent vector field. So these are like the main 2 examples of a dg-manifold. Now, let me introduce what we mean by homotopy algebras. This is the same as an L-infinity algebra. It's just some name. It's just an equivalent name for the same object. And for this, we need a graded vector space L. And when this graded space is endowed with higher brackets, by this I mean these multilinear maps of degree k in this case, that satisfies a generalized Jacobi identity, then this is what we mean by an L-infinity algebra. I know that the equation here is not saying too much to us, but if we compute the first cases for this equation, we will obtain the following. So first, the first bracket will satisfy this property. So we will have that the square of L1 is 0, which means that we can speak about cohomology. So this is giving us a differential. And secondly, the relation between the first bracket L1 and the second bracket L2 is that L1 satisfies the Leibniz rule, which is given here. If you see carefully, we see that this is the property of L1 being a derivation with. And now if we compute the next Jacobi identity, we will obtain an expression that looks like this line here. So the meaning of this is the following. If we consider the cohomology of L, and then if we look at the first line in this expression, we will see that the usual Jacobi identity is satisfied. So the meaning of having an L-infinity algebra, it means that you have a graded Lie algebra in the cohomology of your graded vector space. And one can proceed further, like you can have higher brackets, and then you will have some relations between L4, L3, L2, and so on. One can continue in this way. And we will have like this identity here for the higher brackets. So now there's a relation between these two objects. So we see that this notion of L-infinity-algebra, it looks like more algebraic. It looks from a more algebraic perspective. And now we are going to see that a Q-manifold is encoding these L-infinity-algebras. So this is like a more general approach, and it's more geometric, and it encodes the notion of an L-infinity-algebra. So now let's consider a graded vector space. Suppose we start with a graded vector space, which is endowed with this L-infinity-algebra. Then one can consider or define an nilpotent vector field by this prescription here. So when we take a vector from my graded vector space, V, I define the homological vector field by using the higher brackets of the L-infinity-algebra. And then one can prove that this is homological by using the generalized Jacobi identity that I exposed before. So this expression, which looked like very complicated and messy, it can be summarized by the nilpotency condition of this homological vector field. And now we can do this in the opposite way. So in this case, we see that we are taking an L-infinity-algebra and we are producing a Q manifold, but we can do it in the opposite way. We can start from a dg-manifold or Q-manifold and reproduce an L-infinity-algebra. So to do this, suppose I consider a general dg-manifold, which I denote by M, and let's fix a point on the base manifold associated to this graded manifold M. Then, if one considers the Taylor expansion of the homological vector field Q, one has an expression that looks like this. And what we can do now is that we can define an L-infinity-algebra in the tangent space at the fixed point. So we do this in the following way. We just, for the moment, we assume that the value of the Q field around the point P is just 0. And then by using these Taylor coefficients of this homological vector field in this point P, we define the brackets for the L-infinity-algebra by this prescription here. So if I do this, then again, the condition that the Jacobi identity holds is equivalent to the nilpotency condition for the Q field. So what I'm doing here is I'm taking a dg-manifold M and I'm reproducing an L-infinity-algebra at the tangent space at a fixed point. Now the question is...
Sorry, may
Yes.
I ask something? So
Yeah. Mm-hmm.
For this to work, you need to pick the coordinates so that they have appropriate degrees, right? They should be homogeneous of appropriate degrees.
Yes.
Can you state what's the choice of the degree?
What's the...
What's the degree of xi, for example, so that Li turns out to be homogeneous of degree 1 for every I?
Okay. I see your
Because you
question.
cannot choose an arbitrary coordinate system, right? It has to be graded appropriately.
Yes. Okay, let me think. If you're working in this graded stuff, you have, if we are working with Z2 graded, then you have some even coordinates of degree 0, and you have some odd coordinates, which can be of degree 1, for example. In this case, I think you can, as I understand, you can just mix these, mix the degrees. Like in this case, XA can have even or odd degrees.
But you need to give them a Z grading, right? Because you insist that your manifold is Z graded and that Li have degree 1. So.
Okay, I mean, I'm not specifying the degree here in this discussion.
Okay, thank
you. Okay.
Sorry, if I may also have a question. So
Yes.
with a view towards taming the L-infinity-algebras to the younger members of the audience, could you maybe say in what context they pop up? Otherwise, like there are those special slim L-infinity-algebra, which appear in the context of higher Lie algebra cohomology. Can you comment on how, say, the Q then is special? Is it somehow special? Do you see it? I mean, the works by Baez and collaborators, where the meaning of classes in higher algebra cohomology higher than 2 was disclosed, and then those very special L-infinity algebras popped up naturally, so concentrated in the extreme degrees. Does it ring a bell?
I think I have seen something like this before. Yeah, but I don't know. Like I don't have much experience with this, with what you're mentioning precisely.
All right, so just move on then.
Okay, thank you. So now let's continue. In this discussion, as I was telling you, I was assuming for the moment that the value of the Q field in the point P is 0. So if you assume this condition, you will reproduce an L-infinity algebra which has no curvature term. But in general, this can be not necessarily, it cannot necessarily have to be 0. So in general, you have this constant term, which is the value at P of the Q field. And this is what they call, or they refer to as the curvature of the L-infinity algebra. So now, this construction, as I mentioned before, it's only the fixed tangent space at this point P. And of course, it depends on the choice of coordinates. It depends on the choice of coordinates. And now the question that we ask is natural to ask is, what if we change coordinates, or what if we want to obtain like a global construction, which is like more intrinsically defined? So we want to, in some sense, what we want to do is to globalize this construction. So we want to define an L-infinity algebra on the space of vector fields without just localizing first. So without taking coordinates from the very beginning. And to expose this, the main proposition, the main theorem that I'm going to use was explained by Voronov. So the things that we need, or the ingredients that we need to produce these L-infinity algebras are the following. So we need a Lie superalgebra, which I denote by L. We need also an nilpotent operator denoted by delta. And then suppose we have an abelian subalgebra inside this L and some projection which satisfies a distributivity condition, which is given here. Then one can define an L-infinity algebra on the abelian subalgebra by this prescription. So this is called the derived brackets construction. So the end bracket is going to be defined in this way. So we need all these ingredients. So in my construction, I need to see the space of vector fields of the dg-manifold as an abelian subalgebra inside a Lie superalgebra L. So I will need to tell you what is this Lie superalgebra L and what is the role of this nilpotent element delta and the projector. So these are like the main 3 objects or ingredients that we need to use to apply this proposition. Okay, so let me.
If I can make a remark, I mean, this is just a very particular case of a homological perturbation theorem, right? There's a more general theorem, which is much older, I think, from the early 90s, that tells you that you can induce an L-infinity algebra on a subspace, irrespective of whether that subspace is an abelian subalgebra, right? And this is just the particular case of the theorem for this particular situation in the assumptions.
Okay.
So the theorem predates Voronov's work, I think, by many years. Yeah.
Okay, I thank you for the comment, because I actually didn't know about this general statement. Like, I have been using this. I read some time ago this paper by Voronov, and I knew about this particular case, but I was not acquainted with the general one. So I think it's useful what you're saying.
Yeah, for all these homotopy structures in general, you have appropriate homological perturbation lemmas. So this is one of the oldest examples of this. Yeah.
Okay, thank you. Okay, so now let me show you like in a summarized way the ingredients. Then I will try to go to the details. So first, as I was telling you, I will try to see the space of vector fields of the dg-manifold as an abelian subalgebra. So these sections of Tm is what are playing the role of the abelian subalgebra. And now the space of formal vector fields on Tm, this is what will correspond to L in this proposition. So I would like to see the space of vector fields as an abelian subalgebra inside this L, which are formal vector fields on Tm. So later on, I'm going to be more specific, and I'm going to give you the definitions of what do I mean by these formal vector fields on Tm. So again, to define this L-infinity algebra, I need to construct this nilpotent operator inside L and this projection map.
Sorry, Marta, there is a question.
Yes.
What is this S with hat where you define this space of formal vector fields as sections of a bundle, and then you have S with this hat? This is symmetrization.
Yes. Sure. I should say more. I should say more details about it, and I'm going to do it next. What I mean by this is like the completion. It's like the symmetric completion. So you will have not only polynomial expressions, but you will have like series, formal power series.
Okay, thank you.
It's a graded periodic completion.
Can you say again? I didn't hear.
It's a graded periodic completion. So in general, in the theory of commutative rings, you have a completion with respect to an ideal, the periodic completion. Here you have a completion with respect to a graded ideal. And there's, of course, a topology associated to that if you want. So it's completion with respect to that. I'm just answering his question briefly. Yeah.
Yes. That, I mean, that's precisely what it's the meaning of this hat. Okay. So let's continue. As I mentioned before, to be more specific about it, let's consider coordinates on this tangent bundle of M. So by x1 till xn, I mean the base coordinates on the manifold M. And by this y1 till yn, I refer to fiber coordinates of tangent vectors. So these coordinates are induced by the local frame, induced by x coordinates. And then I think this again is like also replies to your question in more detail. What I mean by a formal function on Tm is just a section of this bundle, which I denote by x hat t star m. So I mean by this section, I mean an expression of this form, which is a formal power series in these fiber coordinates. So we have something like this. These coefficients, which I'm writing here, are just smooth functions on the base manifold. And these are, as I said before, are fiber coordinates. So these y's corresponds to coordinates of tangent vectors. So this is how sections of this bundle looks like. And now what I mean by a formal vector field is just a derivation of this type of functions. So we will differentiate with respect to these fiber coordinates. So okay, I don't want to go too fast. I think I can continue now. Let's continue. So now, by a formal vector field, I mean a derivation of this type of functions. So in coordinates, this type of vectors will look like this expression here. And then I can say the following. I can say that the space of such vector fields will correspond to a Lie superalgebra. And the Lie bracket will be just taking like the Lie derivative with respect to with these y's coordinates. Okay, so now...
they're only vertical or what?
Yes, they are only vertical. Yeah. Yes. Okay, so now we need to see the space of vector fields on this dg-manifold M as an abelian subalgebra of the space of formal vector fields. So what we do here is that we consider expressions in this form. So you see that I'm just taking like the vertical part here. I'm not taking derivations with respect to the base coordinates x, but I'm doing this with respect to the fiber coordinates. So I just identify the space of vector fields on M, which expressions of this form. And then, of course, if you compute this Lie bracket with vectors of this form, you will have that this is 0 because the coefficients are independent on y's coordinates. Okay, so now by the projection, then I do the following. Can you see the formula? I think you can. Okay.
We can.
By this projector, okay. By this projector, I just take an object which is a formal vector field. In general, we know that the coefficient for this vector is dependent on x and y. But what I do is that I set the coordinate y to 0. So this will be a projection onto the vector fields of this form. And then one can prove that with this definition, one can prove that this satisfies the distributivity condition that I need in this proposition given by Voronov. Okay, so do you have any questions in this part?
It seems you can continue.
Okay, continue here. Okay, so now we now have the Lie superalgebra. I have the abelian subalgebra, which is corresponding to the vector fields on M. And now I need my nilpotent element, which will derive the L-infinity brackets. So I need to construct this nilpotent element delta. But in order to do that, I need to introduce some operators which are used in the context of Fedosov deformation quantization. So let's consider first the operator, which I denote by delta. What I do is that I take a section of this bundle. These are just formal functions on Tm twisted by differential forms. And what I do is that I take the derivative with respect to the fiber coordinate y, and I produce the wedge with the differential dxi. So what you see is that this operator is lowering the degree with respect to the polynomial part on y, and is raising the differential form part. So this is what I mean by delta. You can prove that the square of delta is 0. Then I consider another operation, which is kind of inverse to delta. So what I do here is that I, instead of reducing the degree with respect to the polynomial part, I'm raising the degree. So I take this section of this bundle, I take this section, I produce the contraction with respect to del xi, and I multiply by this yi coordinate. Okay, and then to just finish this part, I define an operator which I denote by age. The reason for this notation is because this age, it can be thought of as a homotopy operator. And this age is basically a rescaling of delta star. So if I take a section of this bundle which has m degree with respect to the polynomials y's and k degree for the differential form part, what I do is that I just divide by these degrees and I apply the operation delta star. Okay, and in case that I take something which is just of 0, 0 degree, I just define age as 0, okay? I don't know if you have questions here. I hope it's clear enough. Now that I have these ingredients, I'm going to state the main theorem in this construction. And this theorem basically uses the similar techniques to Fedosov deformation quantization. So in the classical sense, in his ideas, he constructed an nilpotent operator by starting with a torsion-free connection. So here we do something similar. We start with a torsion-free connection on this tangent bundle of M, and then we can prove that we can deform this connection nabla by this form. I can deform it by the expression minus delta plus nabla plus some higher terms in a way that this operator is nilpotent and that this differential form R satisfies the property that is 0 when you apply it to the operator H. Okay. So now I'm going to use this operator d0 to produce the delta operation that I need this delta. As you remember, I want to define this nilpotent element delta to define the brackets for the L-infinity-algebra. So I'm going to use this operator d0 to obtain this delta in some way. Okay. So now with this in mind, we just have an nilpotent connection on the space of formal functions on Tm. What I'm going to do now is, as I told you, I'm going to define this delta. We can see that this d0 operation, it can be understood as a formal vector fields with values in one differential forms. Okay, because this d0 is just taking a formal function on Tm. It acts as a derivation, and it reproduces another formal function on Tm twisted by a differential one form. So this is just a formal vector field with values in omega-1. And now by this, we can see that we can introduce another connection on the space of formal vector fields by producing the commutator. So if I take a formal vector field X and I want to apply the connection D1 on X, I just take the commutator of formal vector fields twisted by differential forms. And one can prove that this is also an nilpotent connection. You can use the graded Jacobi identity for this Lie superalgebra, and you have the nilpotency condition. So now the other main theorem that we have in this theory is that we can have a correspondence between the abelian subalgebra, which I identify with vector fields on M, and and the space of formal vector fields that commutes with this connection D0. So we have this correspondence, and what I'm going to do now is that I'm going to use this correspondence to obtain an element associated to the homological vector field Q. Okay, so we know that on the base manifold M, I have this Q field, this nilpotent Q field, and using this theorem, I can produce some kind of lifting of Q. So I will have some formal vector field which commutes with D0, and this is basically, what I'm going to use as delta. So we, as I said, we just apply these theorems to this homological vector field, which I identify with this vector here, like taking this vertical part. And then I take its corresponding element in the space of formal vector fields. One can also prove that the projection of this lifting is going to be precisely Q. And now we can apply the derived brackets construction. We are going to obtain the following. In this case, I will have a curvature term. This lambda 0 curvature will correspond to the Q homological vector field. Then, if I compute the unary map, this is going to be defined by this projector applied to this bracket of formal vector fields. And this will give us precisely this term that we have here. So we will have the covariant derivative along x of the homological vector field Q. And so on. We proceed for the higher maps. For the binary map, we will have an expression that looks like this. Okay. I'm not showing the precise expression for the higher maps. I'm just telling you that the general formula looks like this if we apply this proposition. The main thing is that this L-infinity-algebra has the property that it has curvature, and that the unary map looks like the covariant derivative along x of the vector field Q. Okay. So now, in all this discussion, we have been using this Fedosov-like connection. What I would like to do now is to see how is this related to another operator, which is defined in this in the product manifold M times M. So for the moment, I will assume that I take a smooth manifold M. I'm not working necessarily with a graded manifold now. Was it like some question here?
It was a cough. No,
okay.
there was no question.
I thought, okay. So now suppose I take a smooth manifold M, and I consider this product, M times M. I have these two projections. If I write x, z as coordinates in the product manifold, then I define pi1 as the projection onto the first coordinate. I define pi2 as the projection onto the second coordinate. And now we are going to use this notation. We denote by m hat the formal neighborhood of the diagonal. So the thing is that we can understand this in the following way. If I consider smooth functions in this type of space, we will have like formal expressions. So we will have, I don't know, we have two variables, x, z, and if we are working near the diagonal, we will have that this x and z, they are close enough, and you can consider smooth functions here. In some way, you can think of this type of functions as a Taylor polynomial of a smooth function on M. So this is that's mainly the idea of this formal neighborhood. And now, if we consider this space of functions on this formal neighborhood twisted by differential forms, we can define an operator which is going to be nilpotent and it's given by these prescriptions here. So if we take this pullback of smooth function on M, and we apply this expression here, this is going to coincide with this pullback of pi1 applied to the differential of H. And then for the other expression for this second projection, we will have 0. If we write this in coordinates, we will have an expression in this form, which, if you see, it looks like a copy of the RAM operator. Okay, so now there is some relation between this expression here and the Fedosov connection that I exposed before. So to see this, let's consider the geodesic exponential map. So suppose you have some manifold M. As I said, in this case, I'm working with a smooth manifold, not necessarily graded. If we fix some connection on Tm, then we can consider this geodesic exponential map, which is, okay, I will recall the definition. Maybe you all know this, but I will say it. Basically, we consider some, let's consider some initial data, like I have a point in the manifold M, and I have some vector, some velocity. And if I consider geodesic, if I consider this problem of the integral curve, I consider some geodesic that starts in this point X and has this initial velocity. Then I apply, I see how this curve moves, and I apply this when the time is equal to 1. So I will see how this is translated, and this is the image of this map, of this exponential geodesic map. It is known that this is giving us a local isomorphism of fiber bundles. So what we want to do now is to, in some way, we want to transfer the formal maps on the diagonal in M times M to formal maps on Tm. So in this right-hand side, we have this Spencer operator, while in the left-hand side, we had the Fedosov connection. So we will have that they are related by a conjugation of this geodesic map. So the main theorem here is that, again, the Fedosov connection that I exposed before, defined in the space of formal functions on Tm, is going to be conjugated to the Spencer operator. And here, okay, I'm going to tell you how this geodesic exponential map behaves when it's applied to these coordinates on M times M. So
I'm sorry,
for
sorry, a silly question. So on the left-hand side, you have the Lie algebroid, tangent Lie algebroid of the pair groupoid, which you have on the right-hand side. Does it, and then Spencer operators appear naturally on Lie groupoids, as shown by Krajnik and Salazar and Stručiner in connection with multiplicative forms. Does it play any role here? Because it's, I mean, it's all in there. So just asking, trying to anchor this discussion in something that I know.
Okay. Well, I'm actually not familiar with this, so I don't know. But
so the structure of the Lie
can...
algebroid on the left-hand side and the structure of the corresponding integrating Lie groupoid on the right-hand side is immaterial for you. Doesn't play a role, or what? No.
No, no.
I mean, if I can make a remark, I think this construction extends to the groupoid setup. But
so to other Lie algebroids with their Q
yes,
and
I think
the corresponding Lie groupoids. Yeah, I would expect it.
It does extend, yes.
Yeah, it should be generalizable, but in this case, it's just the Grothendieck Malgrange construction, so it's not that advanced.
Yeah.
Okay. Okay. Thanks.
Okay. So now in these last expressions here, I'm just kind of showing you how these coordinates in Tm and m times m are related. By this expression here, this block exponential, I just mean the formal exponential of this operation. So we just iterate. We start with the identity, then we apply this operator, and then we have the kth term will be 1 over k factorial, and this expression apply k times to this coordinate xi. So this is how you can understand the coordinate of the tangent vector. So yeah, I think I just mentioned this before. What I'm saying here is that if I transfer how this Spencer operator behaves in n times m, if I transfer this through the exponential map to Tm, we will obtain just the action of the Fedosov connection that I exposed before. Okay, and now
maybe you should start thinking about the right moment to take a break. I'm just throwing this in.
Oh, okay.
But I think that, I mean, if I'm seeing it correctly, there are not many slides to the end, so we can as well. I don't know what's your plan, Valentina, but
as you prefer, because this seems to be like the right moment to break down or up, depending on where you come from. If any break is foreseen, envisaged.
Yeah, but the thing is that like this is gonna be a short talk.
Okay, so let's go. Never mind. So let's go. Yeah.
I think that you typically have this break and 45 minutes after and before the break. But in this case, I'm just finishing with the following. So, okay, so just to finish this discussion of L-infinity-algebras associated to dg-manifolds, there's another construction which is called Kapranov type L-infinity-algebra, and this was exposed by Mehta, Stiénon, and Zhu.
Hello? Anybody out there?
I think we have lost the speaker for a while.
Yeah. Or maybe it was really a very quick ending of the talk.
Oh, I think we have to wait.
Abrupt, I would even say. Hello, Marta?
No, that might be some problem with internet.
Yeah, so since
Okay,
Valentina
we'll wait. So a break
reported, we just wait.
It's a self-fulfilling prophecy then. Let's have a break.
Oh, a break. Yeah, so while we are waiting, Rafa, are you there? No, break, okay.
I am there.
You are.
Always.
Because I thought that maybe I can tell you about this guy.
You can also speak in our mother tongue.
Mother tongue, okay.
No, it's
Dobra,
not.
więc rozmawiałam z tym panem. O, ale Valentina się pojawiła.
She seems to have some problems with the internet.
Yes. Sorry, like it's been
Right.
there's
Do you need
problems
time
today.
or do you need more time, or you're fine?
I'm fine. Like, can I share my screen again?
Forward.
Yeah, sorry for the inconvenience.
No,
because
but
you're disconnected.
yeah, and
Yes.
he lost her co-host status.
Yeah.
Sorry. Now. Może mi ktoś szybko pomóc?
Sorry, so finally break or not break?
No, it's just a cock-up, not a break. Okay, now. Now.
Rafa, what are you doing? You should
I'm
make
doing my
Valentina
best. If you're asking, I'm doing my best.
The screen is very beautiful, but there is no reason for you to share it.
Yeah, okay.
So share your screen, Marta. Now you can share it.
Yeah. But I think you have to stop sharing.
Stop sharing.
Stop sharing. Yeah, I've stopped sharing. Was it good enough, long enough for you all to appreciate? Okay, Marta.
Yeah, okay. Now you can see my
Full
screen.
screen. Yeah, full screen
Yes.
and full throttle, please.
Okay, yeah, I was telling you what we did before. The last thing we did is that I showed this relation between this Spencer operator and this Fedosov connection on formal functions on TM. And now I was telling you just to finish this discussion of L-infinity algebras on these vector fields. I was saying that there is another structure which is called Kapranov type L-infinity algebra. This was exposed by Mieta, Stiénon, and Xu, and they proved that the space of vector fields associated to a graded manifold admits an L-infinity algebra. So the thing with this structure is that they don't have this curvature term. They just define the unary bracket in this way. So we just consider the Lie derivative along Q of the vector field X. As for the binary bracket, this is the so-called Atiyah cocycle. So this is by definition given by this expression here. And it's called cocycle because you can prove that when you apply the Lie derivative along Q of this class, you're going to obtain 0. And also, it can be proved that this is actually independent on the choice of the connection. So it's like an intrinsic object, it's well defined. It's also, at least for future work, it would be interesting for us to study like the role of characteristic classes in all these constructions. So in general, they also have some recursive relation for the higher brackets. These higher brackets are completely determined by this Atiyah cocycle, which corresponds to lambda 2 and the curvature of the connection. So just to conclude, as I told you, this was going to be brief. We just have two different structures defined on the space of vector fields. So in my master thesis, which is what I exposed before, we have this curved L-infinity algebra by using this Fedosov procedure. And in this case, if I take a torsion-free connection, my lambda 0 bracket, corresponds only of this term. So I only take the covariant derivative with respect to x of the homological vector field Q. But in the case of the Kapranov L-infinity algebra, which was given by these authors, they have the complete Lie derivative. So these are like the main differences between these two structures. And I think this is what I was going to show you today. I would like to thank you for this opportunity and thank you for your comments. I think I still need to understand some things. There are some things that you mentioned that I think I did not understand precisely, but I would like if you tell me about these references. Someone was telling me about this exposition given by Kreinig and Salazar. I haven't read their work in these regards, but I think it would be useful for me to see this. Thank you.
Thank you. Thank you very much. Yeah, so I'll forward. I suppose Alexei knows the reference. It's on the relation between multiplicative forms and Spencer operators or generalization of Spencer operators on Lie groupoids, first jet bundles. of local bisections on the groupoids. But
yes,
maybe
I do know.
You do know it, right? I mean,
Mhm.
okay. So any questions?
Yeah, I have a somewhat general question. If you could comment a little bit on the relation between this construction and deformation quantization of Poisson manifolds, as it's usually understood, because here you don't a priori have any Poisson structure, right? Or graded Poisson structure.
No, not yet, but okay, like in my case, let me show you here. Here is the Fedosov light. Okay, like in his construction, he was applying these deformations to produce this nilpotent operator. It was in the context of symplectic manifolds. But what I'm using here is some generalization, so you can also consider this problem when you don't have a necessarily symplectic manifold. But we have been thinking about some future work, so maybe we can consider the case in which we have like a Hamiltonian dg-manifold. And then maybe we can apply these procedures, and we have this question about what type of structure we can define on the space of vector fields associated to this Hamiltonian dg-manifold. So maybe it will be like an L-infinity-algebra with some additional structure, maybe. But I don't know if this is what you meant by your question.
Yeah, so maybe that's better understood than a question for Alexei Kotov. I mean, at this point, it doesn't seem clear that this provides some kind of version of deformation quantization for graded manifolds. Is this what you are aiming for, Alexei?
No, I think it's just some. It's just another application of the Fedosov construction, so it's not.
You're just looking at it as a construction at this point.
It's not exactly the same.
But I mean, what you have in mind? Because I know that you have something in mind, even if you don't want to say very clearly yet. I mean, there must be some kind of purpose that you are pursuing, right? You're not just doing construction for the sake of construction, I'm sure.
No, I think that's what she said, that we can do the same for Hamiltonian Q manifolds, just the same as for just usual Q manifolds.
Okay. Okay. Thanks.
Okay.
I think Volodya was raising his hand. VNS, I think, stands for Salnikov.
Yeah, true, but it seems that the question somehow asked itself. I was curious about precisely Hamiltonian business and the context, and my question would have been like, what do you expect from it? So if someone but Alexei wants to answer it or comment on it.
It seems he doesn't want to say. It's probably premature. So
no, yeah, but okay, then let it be a remark. It seems that it is a natural question.
Okay. Any further questions? Yeah, if there is none, then we thank Martha again for a very succinct presentation. And we reconvene in 2 weeks from now with a geometric take on heavenly geometry. Sorry, with a take on heavenly geometry, celestial geometry. We're going in the eschatological direction, as you can see, but I don't know how far we pursue it. Let's see. So I see you all in 2 weeks from now. Take care. Bye bye.
Bye bye.
Bye. Thank you.
A my, Kaśka, możemy zostać i pogadać, jeśli jest coś. Może tylko wyłączę nagrywanie.